So today we will discuss some another more problems from the uh, uh, EMS, discrete mathematical structure. Establish the validity. Establish establish the validity of arguments. What is argument? I am telling. What is arguments of we have? What is arguments of we have to tell here? What is arguments of P stands to Q stands to R. I am taking here. That is P stands to Q stands to R. That means P R negation of S and the Q. So P of negation of S, that value has become as S stands to R. I am writing here. S stands to R. So, but yes, that symbol we have to write in here. But even though we have to write here the solution we have to take here. P stands to Q stands to R. That is called already yesterday class I told that is called premise. Then P R negation of S also we can call it as premise, and Q is normal, and another one negation of S or P. So negation of S means from the third this condition we have to write here this is commutative law. Why? Because Q is it is equal negation of S or P, we can take that the commutative law. Then S stands to P. S stands to P, we have writing from the above commutative law, we have write implication law. We are writing here implication law. So we are writing implication law, implication that one. So therefore, yes, 2 to 1. So from 1 and 5, what is one premise and what is 5 implication? So from 1 and 5, we have to take it from the above 1 and 5. You can write by transitive rule. Transitive. You can write here a transitive rule. So therefore, next one, S and Q to R from 6 and by condition. So from the above condition, from the 1 to 5 is a from 1 to 5 is a transitive rule. So we can write it is conditional. It is a conditional proof. We can write here conditional proof. Then Q stands to S stands to Q and S. We are writing Q and S. So by P we are writing Q stands to P and Q. Q stands to P and Q. So therefore we have right here again S stands to Q and S. We are writing here S stands to Q and S. From the third one, what is the third one here? What is the third one here? Q. What is the third one is Q? And that the next one is P stands to Q stands to P and Q. It's a more we have right for these two conditions, that is modus ponens. We can write modus ponens. So therefore, S stands to R from 7 10. From 7 means by conditional proof, and this S stands to R we can call it as transitive rule. What I told for the equality of the argument. Next one we have to learn another thing. Show that R stands to S can be derived from the premises R chances can be derived from the premises. What is the solution? I'm writing a P stands to Q stands to S, negation of R to P and Q. So this is the one part we were given the solution I'm writing here. The negation of R, the symbol R P. This is called what is the given here in the problem also. This is called as a premises. Premise. We can take that this is premise. And then or with the second condition we have take the or also we can take that it is a premise. Then P, so third condition P, from 1 and 2 the premise of negation of R or RP, that we have to write that is a P from 1 to 2. From 1 and 2 we can write here disjunctive syllogism. Disjunctive syllogism. So therefore this is disjunctive syllogism. Then a fourth condition, P stands to Q stands to S. This is also called premise. Why? Because P R, negation of R to P also, that is a premise. So therefore P stands to Q stands to S also, it is all called a premise. Then fifth condition, Q stands to S, 3, 4 mod S ponent. We can write here this is mod S ponent. So therefore we can write here from 3, 4 is mod S ponent. Then sixth condition, Q. This is also Q means already we learned in P is a third condition is a premise. So this is also we can write here premise. Then seventh condition we can write here yes from pi 6 from pi 6 Q to S and Q. This is by mod S ponents and R to S we are writing here. So therefore this is we are writing this is conditional. So what we have to write? What is the premise? So it is a disjunctive syllogism or not? And P to stands to Q stands to it is the premise. From what to Q to S, what we will be applied is a 3, 4 modest ponents. So these all these things we have to write in this one. And also in this one, so after that R to S also we have to prove this is the conditional proof. Then consistence of a premises indirect method of proof. What is a consistent method? A set of formula H1, H2, Hn. So at H1, H2, H3 and so on, Hm we are taking here is said to be constant of the conjunction is the truth value T. We can take the truth value PQ to true or false. A truth value for some assignment, the truth values to be atomic variables appearing H1, H2 and so on. Hm. For every assignment of the truth values are to the atomic variables. At least one of the formulas. What is the one of the formulas? H1, H2, Hm is false. So their conjunction is identically false. So then formulas H1, H2 and so on Hm are called inconsistent. Inconsistent we have this one. What is that there? What is the inconsistent? What is this one we have to define here? A set of formula. What is a set of formula? H1, H2 and so on. Hm is inconsistent there for conjunction imply a contradiction. That contradiction we have to write here. That's contradiction. H1, H2 and so on. Hm that implies R and negation of R where R is any formula. So we are using any formula for in this condition H1, H2. But end means they're clubbing the values H1, H2, Hm. So therefore, R and negation of R, that is the value is R value is any formula. Negation of R means it is exact of, we will take true value that is a false of negation. It's a negative. So therefore, the notation is inconsistency. The notation is inconsistent using a procedure called by proof contradiction of indirect proof. But we show that a conclusion. A conclusion. C follows logically from the premises H1, H2, H3, Hm. So we can assume that C is a false consider, but C is false consider we are taking here. C is false consider we are taking here, but negation of C is additional premise. So this is we are writing that exactly what is we are taking here. So the new set of premise. So the new set of premise is inconsistent. So that they imply of contradiction in the assumption of negation of C proof does not hold simultaneously with H1, H2 and Hm being true. So C is true. When we are telling C is true, therefore H1, H2 and so on Hm we are trying is true. When the C is following logically from the premises we are taking, it is a logically premises from H1, H2, and so on Hm, then only we can take that C is true. These conditions should be followed. So one example we will take here. Example, use the method of proof. Use the method of proof by contradiction. We are taking here, use the method of proof by contradiction. We are taking here P stands to Q and R. So therefore the condition given R to S. So these two conditions taking Q and R to S, then negation of negation of Q negation S. So this negation of S, and that means this exact reverse of S. That means where that is negation of P. But solution earlier I told here. Earlier I told here we have to write here negation of P. So therefore we can take the solution here. Solution P stands to Q and R. It is premise. Earlier premise I already told you in the class, not just now. First condition. Then R to S also premise. And third condition, Q to Q and S also premise. Fourth condition, that is negation of P. Negation of P is same value. That is additional premises. We are writing the negation value. Additional premise. 5P is double negation. Why? Because negation of P is P. That is double negation we are writing here. Q and R. Q and R we are taking here. That is one is premise, 5 is double negation. So P to Q, that is called, it is from 1 and 5 we can write here. This is modus ponens. We are writing here. Then seventh condition we are writing or but from the above or means by conjunction. We are writing here. This is from the above condition we are writing sixth conjunction. Then yes, we are taking here. Yes means 2. What is the R to S is a premise. Therefore, from the seventh also we have taken that this is also 2 and 7 as modus ponens. Then ninth one, R and S. So R and S means 7th and 8th by conjunction. 7th and 8th by conjunction we are taking here. So 10th one we are taking here Q and S. So therefore 6, 9 transitive rule. So 6th, 8 we have taken here transitive rule. But and the conditions Q and S and negation of Q and S we are writing. This is separate one from 3. What is the 3 condition here? 3 is negation of Q and S is premise. So therefore these conditions, 10th condition Q and S are transitive rule. So 3 and 10 by it is 3 and 10 by, we can take the conjunction we are taking here. So therefore C is P negation, P and negation of P. So there is a value is called as. So we are what we are telling. So what we are telling is the same conditions what we are using here is the premises. So therefore the conditions are clearly we know that. Another use the contradiction. Use the contradiction. Use the contrapositive argument. Sorry. Use the contrapositive arguments. Contrapositive arguments to verify the valid inference. Valid inference. So valid inference we are taking here. W stands to R stands to S. Therefore W R stands to S. So for the implication, what the implication we are taking here. So P stands to Q. That is the contrapositive. That is the contrapositive means negation of P to negation of Q, negation of Q to negation of P. So that is a negation of Q to negation of P. We are writing here. Suppose the condition negation of S stands to negation of W and R. So negation of S is W to R negation, that value is same. So therefore negation of S and negation of S is S. So that one R negation of W, R negation of R. So I am applying the negation for both one. So therefore S, this one is S and negation of W, R negation of R. Why? Because this is the same value. So that's why we are taking and rule. So negation of W or negation of R, yes. I'm taking this one R by commutative law. We are taking here by commutative law. So therefore negation of W R, that is S. So therefore W and R is the one verify the valid inference for this one. And another one. So the following premises inconsistent. P to Q, P to R, Q to R. To prove that the given premises are inconsistent, we have to show that the conjunction is a contradiction. So prove that the what is the conjunction is there, it is a contradiction or not. We have to prove from this one function. What is P to Q is the premise. Earlier we told that P to Q is also premise. And also negation of Q and negation of R also it is a premise. First taking the premise conditions here, then P to negation of R I am taking from 1 and 2. So these P and R from 1 and 2 it is called as transitive rule. I am writing here transitive rule. And fourth condition P I am taking here. So P is also already, this is premise. And the negation of R, detail we have writing negation of R. So negation of R is 3 and 4. Negation of R is from 3 and 4 premises and a transitive rule. So it is modus ponens. Sixth one P to R, it is premise. The seventh one negation of P, it is modus tollens. So therefore, the modus tollens means fifth, sixth conditions, negation of R and P to R. So that is called as that one. Then eighth one P and the negation of P, that is C. So all the conditions are C here. So therefore, 4 and 7 are, it is a conjunction for this one. So in this inferences and all these one, we have validity and argument is a defined method of establishing the validity of conclusion using the trick table is explained and illustrated. A few last inferences, a statement logic which are useful establishing the validity of a conclusion without using a truth table is this. Without truth table we discuss it here. So therefore, in addition with to these laws, a few logical implications that also frequently used in alternative method are identified, and all of them listed in the what we have taken table. The rules and inferences P, rule of T, rule of CP, useful in establishing validity explained, and the applications of these rules with it together with the laws of inferences, establishing of the validity here of a conclusion from the listed premises is illustrated through a few examples. Yesterday we learned, and today also I told to you. This is the law of inferences and all these things. The premises explained, illustrated here also. Then the principle of inclusion and exclusion and mathematical induction. We can use inclusion and exclusion for mathematical induction we are taking here. So we can define here the cardinality of a set and quote certain examples. The principle of inclusion and exclusion and applications of it. The concept of mathematical induction and its unity. So therefore, we learned earlier, we learned in the school level or higher levels, the concept of steps, types of sets and cardinal number setup. We also studied about the operators and sets like union, intersection and complementation. Union, intersection means union should be club, intersection will be what is a combined value A and B we are writing here. So in this mathematical induction, generalize the concept, we can counting numbers elements in a given number set known as principle in inclusion and exclusion. So that's why we are writing here introduction mathematical induction and the applications. So therefore rules, basics of counting. basics of counting, definition, and example rules. So in we can use this one in daily life also, that using the numbers 1 2 3 and so on, 1 2 3 and so on. These numbers are called as counting numbers or natural numbers. So counting numbers means we have write 1 2 3 and so on. This one we can count as usual. Therefore we can write here this counting numbers. N is equal to 1 2 3 and so on. So if A is a non-empty set means, if A is a non-empty set means any elements is there and the number of elements is set is called as cardinal number. It is denoted by, we can denote it by modulus of A or NA or NA. You can write here A is equal to 1 2 3. Suppose you can write N of A is equal to modulus of A. You can write this is 3. It is 4 here. You can write here this is 4. But even though the two sets have no common elements in their set with these joint sets, but the more number of sets have no common elements, they are said to be paired with these joint sets. Suppose we are taking A is equal to 2 3 5. B is equal 1 4 6 3 10 20. We are taking these a pairwise disjoint cycles. The E1 and E2 said to be mutual exclusive E and E10. There is no common numbers here. So therefore no common elements, no common elements is there. Exclusive events if E1 and E2 happen, cannot happen simultaneously. So therefore this is the disjoint cycles for 3 A B C, not cycle here. So tossing a coin, one example we will learn here. So we now state basics counting the principles, the sum of rule and the product rule, and the multiplication and the addition we have to do. The sum rule. What is the sum rule we have to learn? The sum rule. What is the sum rule? Sum rule means if A is the union of a pair, if A is a union of pair A1, A2, A3, A1, A2, and A3, and so on, AN is there. Suppose modulus of A is equal to modulus of A1, modulus of A2, plus modulus of A3, and so on, modulus of A. So A1, A2, AN are non-empty sets having no common elements here. So therefore, no common elements is there. We can call as this is sum rule, which is known to be principle of. This is known as principle of disjunctive counting. Disjunctive counting. Those are same principle. So the same principle can be also stated in terms of events. So what is events? E1, E2, and so on. En are mutually exclusive events. That is, E1 can occur in M1 number of ways, and E2 confirm way occur in M2. M1, M2 is occurring number of ways. So therefore, En number of occurs means we can write that is Mn is occurs. Mn that's the number of ways. Then we have to write here E1 or E2 or En, that is we can write here M1 plus M2 plus M3 and so on, Mn. This is called the sum rule. What is the sum rule? Non-empty sets have no common elements we are taking here. So therefore, we will take one two examples here. In how many ways we can get some in how many ways can we get a sum 4 or 8 when two distinguishable dice are rolled. So see how many distinguishable. So therefore we can take here, let x1 and x2 represent represent the outcomes when the first and the second dice are rolled respectively. X1 take any value from 1 to 6, so as X2 1 to 6. The dice is there is 6 elements, so 6 is their number. Why if you play the dice, it's 1, 2, 3, 4, 5, 6, any number. So let we can take the let E1 be the event of getting some x1 plus x2 is equal to 4. Why? Because 1 to 6 x1 plus x2. But we can have which can have 3 ways. What is 3 ways? 1 3, 2 2, 3 1. That is a 3 ways we have to know that. So therefore let E2 be the event getting some x1 plus x2 is equal to E8. This is a double. Why? Because 1 or 8, 1 or 4 or 8 given that in the problem. How many cases with 4 or 8? So first one x1 plus x2 is equal to 4 and x1 plus x2 is equal to 8 we are taking. So therefore which can happen 5 ways. So we can take here 5 ways. That is 2 6, 3 5, 4 4 is equal 5 3 and 6 2. This is the 5 ways you can by the sum of rule. By the sum of rule, that is 3 plus 5. 3 first one 3 and then is 5. So the number of ways getting 4 or 8. So this one we have to write from the what is the given problem. Another example. How many ways are there to choose one letter from among the sets? A comma B comma C, where A is equal to A M N, B is equal to B D G, C is equal to P Q S T. So this is the given sets are pairwise disjoint sets, different disjoint sets. So there are 3 ways to select. There are three ways to select the one letter from 3 sets. Set A, 3 ways to select one letter from the set B, 4 ways to select from the letter C. So by the sum of rule, first A is 3, second A B is 3, that 4. That how much number total is 10. So therefore number of ways for choosing letter from set A, B, C, 10 ways we have to check. We can take the 10 ways we have to do here. This is a called sum rule. Product rule. In A and B, 2 non-empty sets. If A and B 2 non-empty sets, then Cartesian product. Cartesian products A and B is denoted by A and B. It's denoted by A and B is equal to A comma B by A belongs to A and B belongs to B. The number of elements in the products is given by N into N A into B. A into B is equal to dot A into dot B. So A into B, what we have to write in the multiple products, dot A into dot B, we have to write here. So the for the instance, let us we can take the some examples here. A is equal to 1 2 3 and B is equal to 4 5 we are taking here. A into B is equal to 1 4 1 5 2 4 2 5 3 4 3 5 we are taking. So 1 2 4 1 to 1 1 to 1 1 1 4. Sorry, this is 1 4 1 4 1 5 2 4 2 5 3 4 3 5. That is we are writing here. So therefore number of A is equal to modulus of A is equal to 3. Number of B is equal to modulus 2 we are writing. So but number of A into B, the 3 into 2 6. 1 2 3 4 5 6 we have get it here, number of A into B. So A into B is equal to A dot B. This is a multiplication process we are doing. This is called product rule. So then, so this is known as product rule. It is, can be extended any number of sets, that is A1, A2, and so on, An or non-empty set. Then the number of elements can be Cartesian products of A1, A2, An is given by, we can take that A1 into A2 and so on, An. It is pi of I is equal to 1 to m, that is AI. We can, the product is also known as the principle of sequential counting. The principle of sequential counting, this can be defined in terms of events. So what is the events? Yesterday I told that E1, E2, E3, E4 and up to so on, En will be happen in small letters. That is E1, E2 and E3 and so on, En. So the number of ways respectively, then the sequence of events, E1 first, E2 second, E3 third, E4 fourth, and so on. En is, you can write here that is the En is nth. En is nth place can be happen. We can write E1, E2, and so on. En, that we can write, that is number of ways. Suppose we will take one example here. If two distinguishable dice are rolled, then in how many ways can they fall? See here, all of you. Let even be the even. Let even I'm taking here. Let even be the event of the first die fall, which can be happen number of 6 ways. That for first it should be 6 ways. Let E2 we have take here. With the event of the second die can fall, which can happen also. This is also 6 ways. So by the product rule, two distinguishable dice are rolled. They are the 2 into 6 into 6. We can write it 36 number of ways. So 2 times are 6. It is a 6 into 6 is called. We can take as 36 ways. We have to take here. Another one we have to write here. Six students are consisting in a school elections for a president, vice president votes. The students with most number of votes will be the president, and the student who comes the second will be vice president. How many different teams are president and vice president? Suppose number of different teams we are taking. Number of different teams we are taking here. Choices for president, choices for vice president. So suppose first one choice is 6, then 5. 5 choices are left for the vice president. Why? Because already one gone to the president. So the remaining is only 5. So therefore 30 number of different terms is 30 we have to take here. This one. How many bit strings are of the length is 7? How many bit strings are there of length? So each bit of binary digit, what is the binary digit we are, what you are using? 0, 1. So 0, 1, this 7 bits we can use 2 ways. So therefore the product of rule, the 7 means 2 power 7 different cents of the length of 7 are. So this one for the one example. The principle of inclusion and exclusion. One theorem we will learn here. The principle of inclusion and exclusion for 2 sets. So if A and B are students universal, we are taking that A union B. A union B, what we have write? Modulus of A plus modulus of B minus A intersection B. Why we are finding A union B? Right them. So that one, this is a statement. The principle of. So let A and B of two non-empty sets. Let A and B be any two non-empty subsets of the universal set U. Then the union, the intersection of the sets. Then the union and intersection of the sets A and B can be represented by Venn diagram. Venn diagram. So I will use the Venn diagram here. This is union. In the first box, A bar of intersection B, second one A intersection of bar between the two one A intersection B. So that is AB. So therefore, here writing here, A intersection B bar, A intersection B, A bar intersection B are mutually disjoint sets. This is separate. So therefore, I am writing here A union B is equal to A intersection B bar plus A intersection B plus A bar intersection B. So I am writing this is a solution. First one, A means A intersection B. Ante A minus A intersection B plus A intersection B. See here, minus and plus cancel, only remaining A here. Plus B minus A intersection B. This is also same. Therefore, we can write here modulus of A minus A intersection B plus A intersection B. I'm separating plus B minus A intersection B. So that's why we can write here A union B is equal to modulus of A plus modulus of B minus A intersection B. We can run from the above one. This one, this is the. So if A and B, if A and B are disjunctive sets, A intersection B is equal to 5. Therefore, A intersection B is equal to 0. The principle of inclusion and exclusion reduces A union B is equal to modulus of A plus modulus of B. This is called sum of root. Principle of inclusion and exclusion. I told of two sets, now I'm telling three sets. If ABC are any three subjects of universal sets U, ABC, then A union of B union of C, modulus of A plus modulus of B plus modulus of C, minus A intersection B minus B intersection C minus C intersection A plus A intersection B intersection C we are adding. So ABC are mutually disjoint sets. We can write A union B union C is equal. We can write modulus of A plus modulus of B plus modulus of C. So we can write that directly. This one for next general statement of principle of inclusion. If A1, A2, and so on, AN are any n sets in a universal set union. So therefore we have to write here modulus of union I is equal to 1 to m ai. So summation of infinity I is equal to 1 ai. Summation of I is equal to j ai intersection aj. The summation of I j k, that is ai intersection aj intersection ak, plus minus 1 whole power n minus 1, that is a1 intersection a2. We have to write one. So here on the right side, the two summations is taken all ij and the integers 1, 2 intersection n. The third summation taken are ij k 1, 2, 3 n. So therefore a1, a2 and so on n usually disjoint cycles. Therefore we can write a1 union a2 and therefore union of an. Therefore modulus of a1 plus modulus of a2 and so on modulus of an. We can write here this one. Then another one, a problem you have to form a group of 10 professors. How many ways in a committee of 5 members be formed, so that at least one of the professor A and the professor B will be included. So now we have taken here. So the total number of professors, what they have given here, total number of professors 10. Total number of professors. The committee should consist of 5 professors. So therefore, the total number of such committees consisting of 5 professors and 10 professors. So we can write TC 10, 5. So that means 10C5. So 10C5 means 10 factorial by 10 minus 5 factorial into 5 factorial. So 10, 9, 8, 7, 6, 5 factorial. You are using 5. Then 5 factorial into 5 factorial. 5 factorial. It is 5, 4, 3, 2. That is 3 to the 6, 6. And then 5 1 the 5 2 the 2 1 the 2 2 the 2 4 the. So multiply here this one. This is 252. Yes, we are writing it. Then there's a 252. We are writing it. Then we'll go to the let A1 be the set of all 5-member committees in which Professor A is included. A1 is equal to C of 9, 4, that is 9C4. What is 9C4? We already write here. 9, 8, 7, 6, 5, 4. 9 minus 4, 5, 5, 4, 3, 2, 1 into 4 factorial. That is 5, 5 get cancelled. 3 to the 6, 6. 4, 4, 1, 4 to the 10. This it is called 126 of this one. Let A2 we have take here. Let A2 be the set of all 5-member committees which Professor B is included. Which Professor B is modulus of 80 is called C9R4. Again, 9C4. Again, I told from the A is the same 126. So therefore, let A1 intersection A2 be the set of all five-member committees. So therefore, in which Professor B are included, we can write A1 intersection A2 C8 3 are right. Therefore 8C3 are right here. Right. 7, 6, 5, 4, 3, 2, 1. So 8 minus 5, 4, 3, 2, 1 into 3, 2. 5, 4, 3, 2, 1, 5, 4, 3, 2, 1, 3, 2, 6. 8, 5, 8, 7, 56 is there. So therefore, A1 union A2, A1 union A2 is the set of all 5-member committees in which as a professor A or B included. So the principle of inclusion and conclusion, A1 union A2 is equal to modulus of A1 plus modulus of A2 minus A1 intersection A2. And right here, that is 9C4 plus 9C4 minus 9C3. That is 126 plus 126, 56 is equal to this called total 196. This is our one.